So today's topic is an example, in all caps I stress one example of a data science flow. This is a question that comes up a lot. People ask me quite often, how I have this new problem, how should I start? And I often get the sense that what people want me to tell them is like, oh, there's this one set of instructions that you can follow, and if you follow the set of instructions, every data science problem will just like melt at your feet, and you'll pass every interview. And unfortunately, there isn't really such a thing. Actually, it is kind of fortunate in a way, because if you had a single set of rules you could just mindlessly follow, then there wouldn't be a need for data scientists. But I found it's not particularly helpful to tell people that, because they still hunger for something concrete to like grab onto, some kind of set of rules or process to follow. And that's why I put together this talk here for this office hour session. It's really my attempt to kind of explain in the most generic possible kind of problem that isn't an NLP problem. It's not a text or natural language based problem. So just with tabular data, how would I start? What would my process look like? What kinds of algorithms would I try? This is really what I'm hoping to get across today. So if you have opinions, questions, anything like that you want to chime in, please do. Especially those of you who have maybe a little bit of experience doing this as well professionally. If you watch this, you have an opinion, you're like, hey, I really disagree with that. Please interrupt me. Please chime in, because I think it'll be super useful for everybody else to hear that, like, actually there's more than one way to do this, and these are the kinds of places where people start to disagree. So really want to highlight, this all caps is there for a reason. It's one example. Don't just use this mindlessly, but hopefully this at least gives you something to start from. And the first step is actually something that has nothing to do with the technical side of data science. And it's something that I think people often forget to do, which is to constrain your problem. When you work in an actual company, you're going to have constraints. You're not going to be able to work forever. You're not going to have an infinite amount of data. You're not going to have an infinite amount of time. There are things that prevent you from tapping into those infinities. And so you want, even when you're making a personal project, you want to mirror that process as well, because you want to get good at those trade-offs. You want to get good at deciding how much time to invest in what directions, and you want to be able to tell the story of how you made those decisions to people you interview with. It's like much more compelling during an interview if you're telling the story of your project and you say like, yeah, so I tried doing this, but like the server costs were way too high, so I had to cut back and do this instead, or I gave myself a certain amount of time and decided to solve the problem in that time, and so as a result I made these trade-offs. So there's a pretty clear like open-endedness to data science problems. If I give you a Kaggle competition, you could probably go on and hack away at that Kaggle competition for like a year or 10 years if you wanted to. You could turn it into a PhD thesis. This, unfortunately, is true of basically all data science problems. So you're going to have to learn to impose constraints on yourself and decide how valuable a given problem is. And the expression of that value is the time that you're willing to dedicate to solving it. So the first point is really you don't have forever in any practical setting. So you need to practice setting time limits. I usually recommend, like with my mentees, when they start, I say, okay, scope out the project, give yourself an amount of time that is a little bit uncomfortable. So you want to say like, maybe 3 weeks to do an end-to-end full stack data science product or project. I think that's actually like pretty reasonable if you want to put gas on the, put your foot on the pedal. 3 or 4 weeks, not a bad place to be. The last thing you want to do is say, hey, I'm going to start this data science problem and like I'm just going to keep working at it until what? Like that's one of the issues. So definitely bound the time. Do not like have an open-ended process along the time axis. But that's not the only way in which something can be open-ended. It can be open-ended on time, but it can also be open-ended on performance. So if you think about, let's say, a product like the Netflix recommender system. Actually, that's probably a bad example. Okay, let's talk about Covet tests, right? If you had an algorithm that could determine whether or not you had COVID, and that algorithm could guess to within, I don't know, I'm not going to say accuracy because anyway, let's say it made a mistake like 1 in 10,000 times, right? That's probably good enough, right? That algorithm is good enough to be used in the wild. So there's some performance cutoff. If you're making a weather prediction service that's designed to be cheap and deployed in a very low-stakes setting, you don't have to be super accurate. As long as you're better, like considerably better than chance, depending on the use case, you can define usually a walk away kind of victory condition. And that's really what you want to do. So once you hit that victory condition, make an agreement with yourself ahead of time that you're going to declare victory and move on. Right? This is really important because otherwise you will find yourself in this vortex where, like, yes, you absolutely can always squeeze another like epsilon of performance out of your system. You will always be able to do that. And you're going to get blinded by it. You're going to get like addicted to the iterative optimization. You're going to get tunnel vision, and you won't see the big picture. You're going to start essentially wasting your time making your algorithm better than it needs to be for the practical purpose that you built it for. So these two things, time bounding and performance bounding, are really, really important constraints on your problem. You want to think about them before you start building anything, right? So tell yourself, how much time would I be willing to put in? Would I be happy with? What's my appetite for this? Set that as a number of weeks. And then separately, what performance threshold? Like if you hit that performance threshold before your appetite is up, before your time bound is up, then great. You've got more time to build other projects, apply to other jobs, talk to other departments, look at more analytics. Your time is valuable, and you really want to reflect that in your approach to this. I think it's fair to say the kinds of decisions you'll find yourself making are, when you do this sort of thing, are going to lead you to develop a kind of experience, a kind of understanding that companies actually care about much more than you might imagine. So when you start describing your projects to companies and saying, yeah, I was running up against my time limit, my time bound, and so I had to like scrap this, or I had to try a simpler model for that, or whatever. These are the kinds of considerations that cause you to actually sound relatable to people who care about delivering things, shipping fast, building for real needs, and so on, like companies, in other words. So I can't emphasize that enough. Like, start by constraining your problem. If you're not doing this, you're opening yourself up for a world of hurt, because you'll find yourself kind of spiraling into this like never-ending vortex. You can always do more. You can always do more feature engineering, try more models, do more hyperparameter optimization. Like, drop it once you hit either the time bound or the performance threshold. Cool. So yeah, this is just a nutshelling of what I said. In general, if your predictive modeling project is open-ended, if you can't tell me when it's going to end, then you're probably doing it wrong. Okay? So like, it really is that simple. Very, very, very rarely is it ever the case that it's okay to tackle something in a fully open-ended way. I'll toss in one last thing. I didn't know where to squeeze this in. So Leo, who's a former Sharpest Minds mentee, he did a couple office hour sessions. He's now a mentor as well. He had this great point, I think the last time or the time before that I gave this particular talk. So he pointed out that one other thing you want to do if you're working in a company, so if you're already hired, try to make sure to get your managers on record with their predictions about what's going on with your data set. So a classic problem that he's encountered many times before is he'll have a VP or some manager who says, hey, I need you to run an analysis on this data set. He'll run the analysis, return the results, and then the VP or whoever asked him to do it will look at it and be like, oh yeah, but that's kind of what I assumed would happen. In other words, they don't perceive the value. So people often don't realize what their assumptions were going in, and it can be useful to get them to pre-commit to those. So anyway, this is just sort of Leo's tip, but I thought it was worth mentioning because it is part of the early stage of the problem before you dive into the technical details. Anyway, so little thing there, especially if you're currently working in data science. But either way, though, I think the main thing is constrain. Constrain in terms of performance, constrain in terms of time. Cool. Any questions about this before I dive into more technically flavored stuff?
I have a quick question, Jeremy.
Yeah.
In terms of everything that you just said, what would be a good way or a good technique to enforce accountability?
Enforce accountability on yourself, hey, I've run up against the time limit, now it's time to walk?
Yeah.
A great question. So I think accountability can come in a lot of different shapes and sizes. I think one of the best, especially if you're at Sharpest Minds, is your mentor. Tell them, I'm going to deliver this by then, and if not, come up with some kind of penalty. You can be as creative as you like, but just telling another human being is a really nice first step. Another thing people do is they'll use social media. So we've had mentees go to Twitter and just be like, hey, holding myself accountable, I will do X by time Y. and that's it. But at the end of the day, the drive, especially if you're in the job seeking stage, it does kind of have to come from within. So a lot of mechanisms can help with the margins, and talking to other mentees can help as well with this. But at the end of the day, it's kind of hard when you're at that stage. Like once you're working in a job, the accountability will come from your manager, and so I'm assuming we're not worried about that. But when you're on your own doing that job search, mentor, peer, social media, that's usually the triad that I'd recommend.
Hey, Jeremy, I'm gonna ask a question.
Yeah.
So in situations, let's say you've sort of staked out, what you think a good stopping point is, and you've poured a lot of time into the project already, and you never really get there by your time limit. And I mean, this has happened to me in a couple of take homes. It's not the best feeling, but in those situations, you're not at work and you can just kind of say, I tried all these things. It didn't 100% work. Here's my results. Like I can explain why I did what I did, stuff like that. But like, I don't know, any other tips you might add in those kind of situations?
Yeah, that's a great question, actually. It's something I should have included explicitly here because it's sort of unclear what I mean by, what's the consequence of that time horizon. So first things first, some projects fail. Sometimes there's like not enough in the data set. There's not enough juice in the data set to actually make a good model or a model that's performant enough to be valuable. That's going to happen in the real world. It's also going to happen when you're doing your job search and prepping your stuff for that. In either case, the answer is the same. So once you reach that point where you're like, okay, my 2 weeks are up, let's say, write it up. So don't just let it crash and burn it. This becomes a case study. There's value in you sharing what you tried and what didn't work, and that way other people won't fail in the same way in the future. You can also share a really thoughtful analysis about what you think might have gone wrong, including what you think might have gone wrong in terms of your time allocation. Like to do this again, I think I would have put more time into data exploration and like narrowed the scope of my modeling steps, stuff like that. That stuff is actually super, super helpful even when it comes to impressing employers. And I think this is something that like a lot of people have like a gut reaction to that, where by instinct you don't want to share failures with employers because of course every data science project you've ever tried has to go super well, and that's the end of the story. But in reality, they won't, and companies actually know and expect that to be the case. So when you can share stories about failures, like that's a really good differentiation vector. Like if you can come to a company and say, yeah, like I tried this and I gave myself a time limit. In other words, you're hinting at the fact that you implicitly understand the idea of constraints, so you can be relied on to act on those constraints, then that's actually its own good sign just to begin with. So write up a report. You'll have something to show for it. You'll have a ton of pretty plots either way, tons of visualizations, correlation matrices, this and that. But your MAE, your R squared, your RMSE, whatever that metric is, just isn't high enough. It just isn't high enough. And you just say that and also tie it into your understanding that like this metric I decided had to be at least this good. That opens room for that kind of business flavored conversation that companies just love to have. So I'm a big fan of actually writing this stuff up, presenting it as a case study, and actually putting it forward, put a spotlight on it. Does that answer the question?
Yeah, for sure. Thanks, Jeremy.
No problem. Okay, any other questions before I move on to? Okay, cool. So that's that's more the philosophy. Again, like it's so hard to remember to do this, and everybody wants to dive in. I'm guilty of this as much as anyone, but I've always regretted it when I haven't done it. You want to scope out your problem. You want to really kind of price out your time. Okay, let's assume that's done. And now let's get to the first sort of pseudo-technical step. It's pretty obvious. So you want to start by engineering what I'm calling here the obvious features. The reason that I'm saying obvious features, the reason I'm focusing on like implicitly this is one subset of feature engineering, is that feature engineering is not like one step. You're not going to like, step one, engineer all your features. Step two, build your model. Step three, win. Like that's not how it works. You're going to start with a certain feature engineering routine, do some data exploration. You might discover, oh, you know what, like maybe there's no correlation between X and Y, but maybe there would be a correlation between X and like some log of Y or Y times Z or something like that. So you want to treat this as an iterative process, but the first step is always going to be, you'll have some obvious features, things like you have a date, right? And you'll know that, okay, I can split that into like day of the week, month, year. I might even be able to pull out like whether or not that day is a holiday, things like that. Sums of money, right, into amounts and currency. Basically, like anytime you have a field that contains information that isn't intrinsically useful in its current form, like a date, if you have the string like September 4th, 1990, like that doesn't actually give you any useful information. You have to turn it into something tabular, something that you can actually work with. So start with that, of course. That's your very first step. At the end of this step, what you should have is still very raw data, but slightly processed such that every column you have is at least theoretically meaningful. You can at least plot it in some way. And once you've done that, you're actually going to make some plots. And this is really, I guess, where the first opinionated stance that I'm going to take will come in. This is my first move. Every time. Scatter matrix. There is nothing you will ever lose by plotting a scatter matrix. So scatter matrix is what? Let me just zoom in a little bit. So what you do is it's a series of plots, just 2x2 plots, so comparing two different features together. And basically, it's a matrix that shows you every possible pair of features, the 2x2 plots for every possible pair of features in your data set. So in this particular example, I mean, I'm using this like iris data set example, so it's really kind of tried and true, but you can see we have 4 different features. There's like, I don't know if you can see that, but this says petal width. Actually, why don't I look at the bottom here? So sepal width, sepal length, sepal width, petal height, petal width. So 4 different features from a bunch of flowers. And so we have a 4x4 matrix. And we look at, like, for example, this column here is sepal width, sepal length. This row here is sepal width. So this plot shows, sepal width on the y-axis and sepal length on the x-axis. And you repeat that all across the board. You're seeing all your 2x2 plots. Here on the diagonals, basically where like the same feature meets itself, so sepal length meets, in this case, sepal length. What you have instead, obviously you can't make a 2x2 plot because like there's no point in like plotting sepal length against itself. So what you're seeing here is a histogram, basically, or a density plot, probability density plot, which essentially is a smoothed out histogram. And what I love about this is it gives you a great high-level snapshot of all your data. And as long as your dimensionality of your problem isn't gigantic, if you don't have like 200 features, in which case this matrix would just become absolutely disgustingly giant, you can always benefit from doing this. I mean, just take a look. Notice, for example, things like, oh, there's this like, I don't know, this blue cluster, pretty well resolved, right? You can see it's kind of like nicely separated from the other classes. So that's a hint that this problem is probably quite tractable, right? Like, there are quite a few of these plots where even the green and orange clusters are well resolved. So probably, you get a sense for how hard this problem is, you get a sense for which variables matter, you just generally get to understand how your data are distributed. And that itself is really valuable because it'll start getting your wheels going, and you start thinking about, okay, can I do without these features? Should I modify this feature? It gets you thinking about the physics of the problem rather than just be blinded by the math. So you don't want to fly blind. You want to start with a snapshot like this. And again, like my absolute go-to is the scatter matrix. Seaborn and pandas functions galore for this. Like you can find a ton of ready-made implementations. Okay, really quick hot take. I've heard a lot of data scientists say this in my defense, but then again, I always somehow these box plots just keep coming up, and like I have a very anti-box plot. What do politicians call it? Platform. I'm running on an anti-box plot platform. Okay, box plots, if you're unfamiliar, I think you'll probably all be familiar with them. They look something like this, right? So you have a data set, and that data set has a mean. So you see this like kind of diamond shape right there. Hopefully you can all see it. Right in the middle, that diamond shape, that represents the mean. You have the median, which is this blue line that goes across. And then you have the different quartiles, represented in this case by the edge of this black box, and then ultimately the furthest quartiles at the top and bottom with these bars here. And like nominally what this is supposed to show you is like, oh, this is how my data set is set up. So you can kind of imagine, you have a plot where probably there's a peak in the middle somewhere here, and maybe this tail down here is a little bit longer than the tail up here because the median is higher sort of at this end. So, you might expect I don't know, it's something roughly like that. So the box plot is designed to kind of break down a distribution into like very simple elements. Instead of looking at a smooth curve, you're looking at a median, a mean, and then 4 quartiles, and that's it. Or yeah, that's it. So sometimes they'll show outliers as well, but anyway, that's the idea. It's a simplification of the geometry, really, of your problem. And I hate box plots. I really hate them with a fiery passion, and I want to show you one reason why box plots are absolutely terrible. And that reason has to do with kind of the tone I was using when I said something like, yeah, you could kind of imagine that the plot goes something like this. The very fact that you're unsure what that distribution looks like is a deep problem. Box plots assume a monomodal distribution. In other words, a distribution with a single peak. So basically something that looks like a bell curve, a Gaussian, right? Not all distributions are like that. And I'm showing you an example here of a distribution that might actually end up basically mapping on to this box plot, but that you probably didn't think would, right? When you look at this box plot, you probably imagine a peak like right in the middle, whereas, oh, somebody's just gonna join here, sorry about this, guys. Whereas in reality, like you could easily have some weird setup like this. So this plot does indeed have 2 peaks. Neither one of those peaks, in fact, the valley, one of the lowest points of the distribution coincides roughly with the mean and the median, right? So you can actually end up getting a completely distorted picture of what your distribution really looks like if you use box plots to summarize your data rather than these histograms or probability density plots. So, this is, again, this is a hot take. I like to share the things I'm opinionated about if at least they help you think about the sorts of things, the sorts of trade-offs you might want to make. So here you're trading off simplicity for knowledge about the distribution. I happen to think that knowledge about the distribution is kind of important, and I really don't like losing it. So anyway, do with that what you will, but I want to pause here and just check in since we've covered a little bit around here. Any questions about this?
Yeah. Hi. I had a question. Can you, if you know any reference for these distributions and statistical methods?
Sure, I'm sure I could dig some up. Yeah, I mean, I think the main point is sort of summarized here. Like you can just see it, right? Like this.
Yeah, you really explained it great. It was crystal clear. Yeah, I was just thinking about more details. Thank you.
Yeah, happy to share that for sure. I'll dig something up. Thanks, Paris. And Nicola, I noticed you. Yeah.
Yeah, I have a quick question. So I usually see the box plots. Like I was using something with one-way, two-way ANOVAs recently, and people really like box plots in ANOVAs. What do you recommend in that sort of ANOVA type of a scenario? What would you use instead?
So I've used far fewer, or actually, like I've never done ANOVA analysis. I mean, I know what it is, but I've never done it like professionally. One of the things with ANOVA, as I understand it, is it essentially tries to pretend that you have a multimodal distribution, and it tries to like guess what Gaussian modes like fit into it. I mean, I think you'll always do better looking at the underlying distribution. It is okay if you have a model that makes certain assumptions, but you like really want to keep those in mind because it's very common. Like I'll talk about this a lot when it comes to. I have an office hour where I talk about linear models, but like it's very common for people to like make assumptions about their data when they don't realize they're making them. And like you can use box plots all day long as you deeply understand that you are glossing over this information, but you want to just kind of keep in mind that that's what you're doing. I guess that would be my answer. I hope that's helpful.
That makes sense. Yeah, I was just curious if you had like, oh yeah, use X, Y, and Z. No, that makes sense.
Yeah, no, it's a great question. I wish I had more ANOVA experience. I've just never tended to use it, unfortunately. Oh, Hadrian?
If I may advocate on the behalf of box plots,
Yes.
I agree. Like it's useless for like distribution or like to visualize distribution, but I've used box plot. I found them very useful to identify outliers, and I know like in some data set I've been working with, it's been really helpful to know like which percentile of the data set to drop, right? So that this way I'm like I stay with like my values are representative, and I'm not like like I'm not capturing values that are the product of like exceptional conditions, if that makes sense.
Totally, yeah. So I think so to Hadrian's point here, like typically what's done, I think I mentioned it earlier, like you'll have outliers as well that are included. So usually people will, with a box plot, show like the median, the quartiles, and then like a couple points up here that just don't fit in the median or the quartiles. Yeah, so this is, you're right. It's a like quick and dirty way of like identifying what the outliers might be. It actually doesn't always work great, especially when the distribution is particularly like messy and skewed or things like that. But it is a good first order check. I guess my take with that is more or less like, effectively you're using the box plot at that point just for the quartiles, like the upper quartiles, and it's fine. Like it's just that I have yet to see a use for the visualization itself that supersedes, like, I guess the value that I personally have seen from probability densities. But I agree. I mean, there are those marginal uses. Yeah.
Even when it's played as like a time series, you don't think it's super helpful? Like when you, like, for example, you play, like, let's say you're playing Precipitation over like a year, and like each month is represented through like a vertical box plot. You don't think that's useful to have, like, to be able to see on the fly like how quartiles and the median might change that way?
So I think one of the key things there is because that's a problem that you could reasonably assume does have a monomodal distribution. Like it's kind of hard to imagine why precipitation, like I'm not a meteorologist, but I'd expect precipitation to be monomodal, not to have two peaks, for example. Like in that case, it makes perfect sense, but only because those assumptions happen to be verified. It's precisely in the cases where you're, like here, being introduced to a data set for the first time and just doing some initial EDA, that when people tend to use box plots, like they tend to miss out on like, yeah, but what if the data was really weird? And often that's explicitly what you're looking for. So nothing wrong, certainly, especially once you know that your data generally is monomodal, box plots are great, right? But it's like, I guess I'm referencing box plots in the context of new EDA. Like you're introduced to a new data set, you're trying to solve this problem from scratch. If it's an established problem, yeah. But I think that's a really good point. If you do have a reason to think that it's monomodal, yeah, it can be a great summary plot, and I should eat my words.
Hey, Jeremie,
oh, sorry, Mochin. Sorry, Mochin. It sounds like there's a lot of background noise at your end. So I'm not really able to hear. Sorry, if you don't mind writing your question in the chat, and we can get to it there. Sorry about that. The background noise was really loud.
I was gonna. Oh, go on.
Yeah, Nicola, no, go ahead.
Yeah, so I think two things that I thought of. I think it's actually interesting about outliers and box plots. There's some sort of underlying heuristic that I can't remember on top of my head on how you calculate outliers in statistics by default. And I think that's usually what it's shown when you have a box plot. So it's pretty good practice, I think, to make sure that those heuristics make sense for what you're doing. And I think when people use box plots, they often kind of, or ANOVAs or anything, they're like, oh yeah, there's central limit theorem, so it must be monomodal. So they're very heavily, at least I've been reading up on a lot of statistics recently because I need it for work, and everybody is very heavily reliant on central limit theorem when they do anything with presumptions that it's monomodal, because they're like, oh yeah, everything can be simplified to Gaussian, which I don't think it's actually true always in practice. But that I've seen box plots being used and then justified by central limit theorem.
Yep. No, you're absolutely right. So the hope is, right, like if you think about the data you have here, like you can quite often, in fact, even in this data set, which like nominally this is the IRIS data set, it's supposed to be as vanilla as it gets. Arguably, like you're seeing maybe some some multimodality there. Up and to the right, we see with this green curve, there's like another hump here, and there's enough data that might be meaningful. It's hard to tell, but I guess bottom line is you absolutely do see quite often these multimodal behaviors, and though it's worth keeping in mind. Sorry, and then Mochin says, can box plot be used in feature selection, maybe combined with collinearity analysis? I think that there are almost always better ways to go. It's a great question, and maybe we can take it offline as well on Slack, because I do want to make sure we're able to get through this, but I have a feature selection office hour, and maybe that's the best place to address this. I'm biased to believe that there are better ways to go, almost always, but if you're satisfied that the central limit theorem applies, and if you're satisfied that in other words, your distribution is monomodal, is Gaussian, then yes, by all means. It just happens to be the case that quite often those assumptions break down, and when they break down, they can really take you for a spin if you're using box plots to simplify your analysis. But all the points on box plots I think are really good. You're right, there are edge cases. If you're tackling a new problem from scratch, I guess I will maintain that initial position with respect to that assessment. So I'll park the thought there. Okay, next thing. So step 2, I call this plot everything you can, and I guess I really mean this. Like you'll have a couple of plots that you'll go for that are high level plots, and you want to set aside some good time to do this. I think it's just good for developing an intuition for how your data work. Here's an example, correlation matrix. I think most of you are very familiar with this. I will super quickly summarize. So if we look over here, like the correlation matrix looks at 2 variables, and it tries to make a line of best fit through the cluster of points that those variables are associated with, and the closer, basically the R squared of that line of best fit, that's what appears in the correlation matrix. So, or sorry, not the R squared, the R value. So if an R is 1, that means the relationship is perfectly linear. If the R squared value is negative, that tells you that they're inversely correlated, but it still means that they are correlated, so it's a good thing to keep in mind. And then an R value of 0 just tells you that there's no correlation whatsoever, no linear correlation whatsoever. That's really important to keep in mind. So if your data, for example, are related in an exponential way, or actually if you have x and y, imagine you have a distribution where for small values of x, y is small. As you increase x, y gets higher, and then as you increase x even more, y drops again. Okay, so you can imagine, for instance, this would be on the x-axis weight, and on the y-axis ability to play soccer or something, right? Or ability to fight in mixed martial arts, something like that. So really light people can't fight very well in mixed martial arts. As you increase the weight, they get better, but then at a certain point they get overweight and their cardio is no longer good or something, and it drops off. There's some optimum. So if you imagine a distribution that looks like that, if you try to fit a straight line, a line of best fit to that distribution, you're going to end up with something that doesn't fit very well at all. In other words, your R value is going to be absolutely terrible, right? So you will have the illusion, even though these two things are correlated, as I've described, there is a causal link between the two, you're going to end up grossly underestimating the extent of that correlation if you're looking at the correlation matrix. So again, this is an instance where you want to keep in mind the assumptions that are going into this. The correlation matrix is going to tell you how linearly correlated two features are. Often correlations at least have a strong linear component. So even if x and y are, there's an exponential relationship, yeah, a straight line will generally fit decently at least, and your R squared value will be okay. But you want to keep this in mind. What you're seeing is a lower bound estimate on the correlation between features. But it's still a nice way at a glance to quickly say, oh, okay, this, I need to look more closely, for example, at in this case, displacement and cylinders, because they seem to really be closely related. I wonder why. In some cases, 0.95, that R value is so high that it's almost like displacement and cylinders are they're redundant, so you could probably ditch one, right? So this even ties into feature selection. And again, we'll have a feature selection office hour at a separate time, but correlation matrix, definitely, again, one of those high-level things. You're looking at a single plot at all your features together, getting a really quick overview of what's what. And I'll just flag, this only works, of course, for continuous variables. Doesn't work for categorical data, of course, because you can't put it in a correlation matrix. Related to that, what do you do with categorical variables? You set up a histogram. So make a whole bunch of histograms, right? You really want to plot the high level, just the patterns, the distributions of these variables and how they're correlated. So the scatter matrix tells you how they're correlated, and then histograms tell you how they're distributed, and then correlation matrices also speak to correlation. So it's just those two things. What's my distribution for each feature, and how are they correlated together? I mean, this is a great example of like absolutely like garbage data visualization, because so they're doing a histogram. I guess they're breaking it down by sex here, so men and women, and then hair color, and then conveniently blue eyes are indicated by the yellow bars, brown eyes are indicated by the blue bars, green eyes are indicated. So anyway, just like really bad visualization, but you get the idea. So do histograms, correlation matrices, and scatter matrices. Once you've done those three things, you should be covered for all your continuous variables, all your categorical variables. You should have at least some overall picture of what you're doing. Dive into it. Ask yourself a little bit how things are correlated. See if it makes sense to you, at least at a surface level. And this can also be a great time to spot features that you have no idea what they mean. Like, for example, I have no clue what like sepal length is. I don't know what a sepal is at all. I don't know how to garden. I'm not an expert on irises. So, I might just Google that and be like, what is a sepal? Let me see some pictures. And then hopefully it'll make sense why that's correlated to things like petal length and petal width and so on. But it's just something to keep in mind. So this data exploration piece, this is like your first hint at where you need to dive into more detail in terms of developing subject matter expertise. Any questions on whoop, I keep going back to Firefox. Any questions on this? Great question. So Matin asks, what if you have like 100+ features? Okay, so if you have 100+ features, like your scatter matrix, it's gonna stop being useful pretty quickly, right? Like 100 features would mean that you have 100 times 100 is 10,000 plots to look at, and like you don't have time for that. And likewise, your correlation matrix is going to be an absolute monster. So the very first thing you need to do if you have 100 features is you need to get rid of features. And there are a whole bunch of, so this is more of a feature selection question, but I'm going to give you the Coles Notes version. So first thing, ditch features that are like not obviously important. And by obviously important, I'm really calling on a lot of subject matter expertise. Like hopefully you know enough about the problem to know like, okay, these things, not important. Another good way to do this is, so you look at something like a correlation matrix, and what you can do is say, okay, if I have two features that have a really high correlation coefficient between them, like I gave that example of cylinders and displacement, here it's like 0.95, that means like if you plot cylinders versus displacement, like that plot is gonna look like a straight line. That is super straight liney, which means if I tell you the displacement, like pretty much I can tell you the number of cylinders right away, which in turn means displacement and cylinders are kind of redundant, so you don't need to keep them both. So this is one way to pick features in a really simple way, such that you could discard a whole bunch. Another is look at the thing you're trying to predict. So imagine, let's say we're trying to predict acceleration, right? This variable at the end. One quick and dirty way to do this would be to say, okay, if a variable is important enough for me to keep, it's going to have to be correlated according to this correlation coefficient. It's going to have to be correlated to the thing that I'm trying to predict. So we're going to assume that if something is not linearly correlated to acceleration, then it's not worth including. That makes a whole bunch of like sub-assumptions. Obviously there's linearity, this only tracks linear correlations, but it also assumes that like you're only interested in direct correlation. So like, for example, maybe let's pick a value that's pretty low here. So weight, right? Weight seems to have, that number here is 0.42. So weight and acceleration have a linear correlation coefficient of minus 0.42, right? So that means like, kind of fuzzy, the plot doesn't look very like super correlated. You might be tempted to say, all right, then let's ditch weight, right? The problem is sometimes a single variable might not be directly correlated to the thing that you're trying to predict, but when you combine it with another, like maybe when you combine weight and horsepower, it turns out that like if something has a really low horsepower but a really high weight, then its acceleration is this, and if not, it's something else. So sometimes those feature interactions, they can get lost when you're just looking at this like 2x2, comparing one feature to another, which the correlation matrix does. So anyway, a couple little caveats there, but the bottom line is when you have 100 features, that's just too many features. You got to start cutting them. You got to cut in a dirty way sometimes, and that can just mean like hacking away mercilessly with correlation coefficients. That's usually like the first strategy, and then use your subject matter expertise as much as you can as well. I hope that answers the question. Yeah, great, no problem. So I'm just going to check the chat really quick to make sure I'm not. Sweet. Good, good. Okay. Right, okay, cool. So onto my specific data science flow. I think the real question people are getting at when they ask me to share this is like models. Like, what models do you use? What model should I use? And I've got to tell you, there is no answer, and this is like my particular approach. You will end up developing your own, but I'll just tell you what I do. So first thing I would do if I had tabular data is I would make a simple decision tree. And by simple decision tree, I don't mean random forest, I don't mean gradient boosted machine or XGBoost, I mean a literal decision tree. And I would train it on my data, on a training set, and then I would visualize it. So I just take a look, like, hey, let me poke at this and see if all the different branches make sense. This is a great way sometimes to spot like obvious trends in your data, like, oh, it looks like it's very useful for the tree to split on this feature first. I wonder what's going on with that feature, and then maybe you flip back and you go to your scatter matrix and you say, oh, okay, I see why. That feature seems highly correlated with the thing I'm trying to predict, blah blah. So as much as anything, this is a baseline. It's a sanity check. It's a way of getting a number for the accuracy or the recall or whatever value it is that you want to optimize for. This is going to give you that initial baseline. So that way you kind of know, okay, if I score above this level, then I'm doing well. And it also tells you, like, if this little dinky decision tree already solves your problem so well that like you don't need any other models, this could be your victory condition, right? If you have a victory condition decided on, like we talked about earlier, and you meet it with this decision tree, like, don't keep working, you're done. Like, you have your model, right? So anyway, just a thing to flag there. This is your first piece of contact with the possibility of walking away a winner. Cool. Right, I should mention, I usually just look at the first 3 layers of the decision tree. So I would recommend doing the same. Obviously, your decision tree, depending on how much data you have, how complex your problem is, it can go on like basically forever. So you want to just limit your analysis. In my case, I like to limit it to the first 3 layers, just to give me that intuition, make sure nothing crazy is going on. Right. Then I like to do a sanity check. And decision trees have this nice property that they should be able to memorize your data perfectly, with some very specific exceptions that you can almost always ignore. So I just like to make sure that that's happening, that I can get to 100% accuracy on the training set with my decision tree. This isn't a super important step, but it's just kind of like confirming that there's nothing weird going on with your data. It's almost part of like debugging your code, where your code is actually the data science algorithm. Okay, so I'll just pause there and ask any questions about this initial decision tree thing. Okay, cool. Great, so here we are again, feature engineering. And like, I'm deliberately adding this step here, but like it'll always be in the back of your mind as you do this. You did an initial sweep in this process. I guess it was like the first step that we did, that initial sweep. Now we're looking at like, okay, I've had the chance to interact with my data a little bit. I've had the chance to plot a bunch of stuff. I know what some of the correlations are in my data. I wonder if it'd be worth creating some new features. This is usually when I start doing that. You'll have dug into, just like we talked about, you look at this plot, you're like, oh, that's cool. What is a sepal length? I wonder what a sepal is. Google that. That might give you ideas about new features you can engineer. And this is a good moment to do it. So you'll be doing it throughout, but at least include an explicit check at this point. And after I've done that, I now have a data set with like a pretty reasonable feature set, right? So I have some features that are engineered. I also know what performance level I should expect, like how hard my problem is, because I made a decision tree. And oh, sorry, somebody just sent a message. I missed the beginning. Can you explain? I missed the beginning. Can you explain? Oh, what to do by victory condition? Sorry, by victory condition, I mean before you start your project, you should decide on a level of performance that you're going to hit, where you'll just say, okay, that's good enough for me. Like, I declare victory. Otherwise, you have an open-ended project, basically, and you can keep optimizing forever, and you'll end up wasting your time. So you want to really figure out how good is good enough, decide what that threshold is, and once you reach it, you walk away. And you have to kind of make that contract with yourself up front. So now we have this feature set, and this is my next step. I make what I call a respectable baseline model. So for me, it's a random forest. I like random forests because they are stupid simple. They're very easy to understand. It's you always know what's going on under the hood, and they're also, fortunately, quite performant. So for most problems, like if a random forest struggles with your problem, that's a hard problem. Like there's no two ways about it. It's either it's a feature engineering problem that you're going to have to dive into more deeply, or maybe it's a problem that requires some kind of priors about like time series behavior or something like that, neural nets, that sort of thing. But like a random forest is a good model. It's very robust. It should give you pretty good results. So I apply that. Notice that I have not said anything about hyperparameter optimization. A random forest that you import from scikit-learn with no fine-tuning often is going to do reasonably well, right? It's going to give you at least a sense of how hard your problem is. So I have not done any hyperparameter optimization just yet. I just throw my random forest at this. And again, it's a baseline. It'll probably perform better than your decision tree, but it is just a baseline. Again, you check, did I hit that victory condition? If not, keep going. If you did, hey, congratulations, you get the weekend off. Okay, next step. I am a huge fan of using permutation feature importance. So I just want to emphasize, we have probably too many features right now, right? Probably have too many. So to Mochin's question from earlier, I'm sorry, I hope I'm not mispronouncing your name. He was asking, what if I have 100 features? Then yeah, you probably would begin the whole thing by doing something like using a correlation matrix to just hack out a whole bunch of unnecessary variables, or use subject matter expertise to do the same. But assuming you have 20 odd features, 30 features, something like that, and you can actually make a scatter matrix and go through this whole process, you still you probably have too many features. You have features that you can ditch. Excess features are really bad because they distract you. They cause your model to overfit, and they confuse the heck out of stakeholders too, because they start seeing all these different features. They start to think that they're all important when they're not necessarily. So at this stage, I like to just do an initial sweep for feature importances. And the way I do that is using permutation feature importance, which I'll explain super briefly here, but again, there is an office hour session on feature selection, and we'll go into more detail there. Basically, the way permutation feature importance works is you take your data set and you pick one column. So let's say in this case, we're trying to predict athleticism using height, weight, and arm span. And you pick a column that is part of your inputs, and you shuffle it. So you take the entry that was in position in row 1, you move it to row 3, take the entry in row 3, move it to row 9 comes to row 7, or whatever. So you just shuffle that whole column, right? Essentially, you're destroying the correlations between that column and all the other columns. The correlations, in other words, that your model would have used to make predictions. And then you run your model on that messed up data set. Now, you should expect that your model's performance will drop, right? Because you've taken one of these columns and you just nuked it. There's no more information in it. But what if your model's performance actually doesn't drop, or doesn't drop by much? Well, that should be a hint that that wasn't a very important column, right? You just shuffled it, you nuked it, and your model's still predicting roughly as well as it did before. So that's a big hint that, yeah, you know what? I can do without that column. And that's exactly what permutation feature importance is doing. It basically iterates through all your columns, tries to use the shuffled column data set to try to make predictions, and depending on how much the performance drops, like the accuracy or the recall, whatever metric you care about, it will then say, okay, this is the most important feature, this is the second most, and so on. So start by doing that, run your permutation feature importance. The reason I really like this approach too is it's model agnostic. In other words, at no point during the description of how permutation feature importance works did I ever have to tell you I did this with a random forest, right? You could do this with anything, a neural network, a logistic regression, anything that you like. So it's just really flexible, and whether or not you want to use the random forest approach here, this will still be a good step to kind of refine the feature set. So you want to do that, and once you've done that, you want to decide, okay, I've got a score for the importance of all my features, and I need to decide a cutoff. So pick what that cutoff is. Decide what important means for you. Like important for me is like either the top 10 features or it's above this level of importance and so on. And then anyway, once you've done that, you just ditch the ones that aren't important and you've completed your feature selection. And then you have to retrain your model, right? So you've just reduced your data set down to just the features that you've decided are important. And now it's time to retrain it, right? You got to make a new model that just focuses on those. And this is very counterintuitive, I think, especially for people who get used to thinking of machine learning models as black boxes. Like you kind of think like, hey, but I gave you more columns, I gave you more information before. Why are you giving me like a better performance now that I've trimmed that down? And it actually does happen. I mean, it works surprisingly well. When you ditch the least important features, effectively what you're doing is you're allowing your model, in this case the random forest, to like focus its attention essentially on fewer features, but features that are actually important. And that allows it to learn more of the nuances of how those features are related, because it's not distracted like by looking at 50% more features or 100% more features. So anyway, this stage will likely see an increase in the performance of your model, and worst case scenario, like hopefully you won't see a decrease. And if you don't see a decrease in the performance of your model, then that tells you that that reduced feature set is like a good summary of your problem, that you don't really need those other features. Cool. So this is another great time to stop and ask yourself, all right, I've now done my feature selection. I've got a random forest model or whatever model you like to go with. It's pretty optimized here. Do I need to squeeze more? Am I at that performance threshold? Can I declare victory and move on? Or do I have to throw more time at this? Do you have time is a really important part of this question, right? Because you decided on your timeline. Before you ever started this project, you decided on that timeline. You want to revisit that here. Like, do I have more time to push forward? And do I need to do more? And if the answer to either of these is no, then you stop, right? It's a pretty simple loop break. One thing I'll point out, still, Jeremie has not mentioned at any point hyperparameter tuning. He has never said grid search CV. He has never said random search CV. He has never said Bayesian optimization. He's never said any of those things. And that's because quite often you don't need to do them. And this is something that's like surprisingly frustrating to learn, especially when you get excited about that step. Hyperparameter optimization can make a big difference in some cases. Generally, it doesn't. And usually the problem is more on feature engineering or something earlier, like your data just isn't clean enough. It's rare that you're going to see a transformation in model performance just thanks to hyperparameter optimization. But if you have more time, here are a couple of different things that you can try to do. So first off, collect more data, engineer more features, try different models, try model ensembling, and sorry, I should have included hyperparameter optimization. I guess I was philosophically thinking try different models. I mean, really, when you change hyperparameters, it is a new model. And you can argue over how new or how different, but that's where I would put hyperparameter optimization. It's not the first thing you should do. If your thing isn't working well, don't just the way I think of hyperparameter optimization, it's almost like just being really frustrated with your data set and just like grabbing it and shaking it until something comes out. Like something often comes out, but it's more likely to be pennies than like $20 bills. So, take that with a grain of salt. Worth doing if you get to this point and you need to do more. But quite often, this step will give you a decent result. And definitely, if you have to go beyond this step here, you're now into interesting problem territory. And there's no shame in facing this kind of problem. It just means that you have to do more of like one of these four things. I'll park the thought there. Any questions about that or any other aspect of this flow?
Real quick, Jeremy. So,
sorry, Hadrian, go ahead first.
Mine is real quick. I really like the whole sanity check method, but this will only work on classification problem, right? What if I'm trying to achieve I'm trying to predict a continuous variable? I can't. That's not going to be the same. Like it's not going to work in the same way, right?
So actually, this is a great question. Random forests work for regression and decision trees as well. So you can use this for both categories of problem. The biggest limitations to this method, I think, would be like image data, natural language data, things that would require some pre-processing up front, which we can cover at another point. But yeah, does that make sense?
Yeah, sure.
Cool. Hey, Gabriel?
Yeah. So I had a question about these unsupervised learning techniques. Say, if I were approaching the iris dataset and I didn't know anything about the iris dataset, and in the initial EDA, I noticed that hey, there appears to be some way of stratifying, my classification, if that makes any sense. To your mind, do you think unsupervised learning could play a role in feature engineering at this stage, or do you think that's something I should only consider like way down the line?
That's a really good question. I think different people will differ on this, and there's a missing layer of this, which is, in fairness, the scale of your problem. So a good example when you're dealing with like a low dimensional problem like the iris data set, where we're able to lay out like all 4 dimensions and it's not really a problem. It's almost not clear why you even need machine learning for this problem, because like the things just resolve so well in simple 2x2 plots. Like I would argue it looks like petal width and like petal length here. Like you could make a really decent classifier that just like goes, okay, cut here, and you're done. But yeah, so clustering analysis, unsupervised learning, tends to be really useful when you have very high dimensional problems that like you can't visualize very well. That can be quite useful. I think if you start to hit like higher dimensional problems, yeah, like give it a shot. That would be a completely separate flow. You'd have to do clustering, and then you'd have to do like PCA or some kind of dimensionality reduction to visualize your clusters and kind of make sense of them. But it certainly is a good idea. I guess I just didn't cover it in this particular flow. But yeah, it's a really good thing to flag.
Thank you.
Yeah, no problem. Any other questions?
I had just a question about like basically like cross-validation, or basically just whenever you're gauging model performance, if you're getting like a wide range of different returns depending on when you run it, how do you approach that?
A wide range of different returns.
So like if I train it one time and even if I'm doing a cross-validation and I get like a 44 average percent, and then next time I run it I get 39, it's hard to trust that the data is having a consistent return at that point, or the model is performing.
Right. So this would be like because there are a lot of places where randomness could enter into this. Actually, I'll give you an example of one situation like this that my fiance just ran into. So she's doing a PhD. She's doing geochemistry, and she has a data set, and that data set doesn't have many points. It's got like 130 points, and she's trying to build a random forest for it. The problem is that she has to do a train test split, because she does want a holdout set, and like when you have 120 points, like I think her holdout set is something like 30, 35 points, right? Because she's really she needs as much as she can to train the model. The problem is, if you're going to pick out 35 points out of 120, like the odds that you happen to pick an easy set of 30 points or 35 points that just happen to be easier to classify or to do your regression on, like the odds are pretty high. I mean, it's kind of like, if you're doing a poll of 100 people, or you have 100 people in a village and you're trying to predict the outcome of an election by polling like 10 people, the odds are going to just happen to pick like 10 liberals or 10 conservatives just because that's who you happen to get, like quite high, right? So what she ended up doing in her case, which I would actually advocate when you're really data limited, is try different train test splits and literally like repeat this process, like do this whole process on loop, where you end up with basically like a distribution of different model performances on the test set for like your best hyperparameter optimized model, if that makes sense.
Yeah. So kind of just take it to whatever level of complexity you need to kind of get some consistent results and be able to visualize how it's doing.
Yeah, exactly. And like in this case, it's really much more common for this to happen if data is super scarce. If you have a representative, if you have a large enough testing set, in principle, you should get you should start to regress to the mean. There shouldn't be that much variation.
Sure.
Yeah.
Thanks.
Yeah, no problem. Nicola?
I think there's now that you remind me, if it's a limited data set, another thing that I would take a look at is stratify sampling and different sampling techniques, where you, in the village example, you want to make sure you have when you're sampling your data and trying to test it on whatever, make sure that it represents the actual population the best that it can. So there's a bunch of, this is usually like a purely statistician thing, but there's a bunch of, actually Chip, I think, on her CS 239 class or whatever, she has slides and notes on how to do oversampling and undersampling and stratify sampling when you have a limited data set. If you have a bunch of data points, probably going to be fine. But as Jeremie said, if it's a very small data set, you got to fiddle with a lot of that stuff. So stratify sampling might help.
Yeah, actually, that's a really good tip. Yeah, thanks, Nicola. Yeah, and Paris?
I just wanted to ask, what score would you say accurate for in terms of like classification problems?
Oh, I love this question. Okay, so yeah, damn it, I was going to include a slide on this. Okay, this is a question that comes up all the time. Yeah, people ask like, okay, you told me set a victory condition. What should my victory condition be? For like what's a good accuracy? What's a good precision? And unfortunately, the answer I have to give you is I don't know. It depends entirely on the specifics of your problem. Just to give you a couple of examples. So if we imagine a test that's designed to assess whether or not somebody has like a super serious terminal disease, right? That test, like we absolutely want that test to be highly performative. The bar is very high. Certainly, we want to make sure that our false negatives are really low. You don't want to accidentally be telling somebody who does have this condition, especially if it's treatable early on, that they don't have the condition, right? So that's like, I don't know what performance level you want, but it's not like 80%. Like you need to be hitting way higher than that. And then conversely, like there are a lot of way lower stakes applications. We talked about the silly example I gave was like the weather in a fairly low stakes thing. Like maybe you work in a non-profit that I'm not too sure. Anyway, you can imagine low stakes application for weather where, if you're able to predict like whether or not it's going to rain to within 20% probability, that would be really good. Like I'd be like, that's a great algorithm. It also depends on the context of your problem. So if you have a whole bunch of different, take ImageNet. So this is a classic computer vision problem. You have, let's say, 10,000 possible classes that you're trying to sort images basically into one of 10,000 different categories. Like, is it a pig? Is it an airplane? Is it an iPhone? In those cases, you also have to adjust your expected performance threshold because like it's correspondingly higher or harder for an algorithm to do really well when there's so many different possibilities. So it's a bit of a mix. The short answer is I always recommend trying to think as if you're a customer of that recommendation product. So if you're going to build something, like how satisfied would you be if it was wrong X many times out of Y? Like that kind of thinking is going to guide you towards defining metrics in a way that's a little bit more accurate. Hopefully that helps.
Amazing. Thank you so much.
Yeah, no problem. Any other questions on this?
I had a question, Jeremie.
Yeah.
Yeah, so especially for this, at a high level, when you're presenting to customers or clients, they don't care about the statistics, but they care about how is the feature impacting a particular thing, like let's say fuel efficiency, whatever that might be. But like feature importance, coming out of random forest, that's just feature importance 1, 2, 3, 4. They're like, okay, but how much does this impact my fuel efficiency? How do you how do you tackle that problem? I know it's very easy in linear regression because it exactly tells you how much each feature affects your outcome variable. But in other algorithms, is it just going to be a black box, or are there ways to deal with it?
Yeah, this is a great question, and I think it's like, in a way, it seems like two sort of sub questions. One of which is like, how do I convince a customer or an end user that I've built something valuable? And then another that's like, how do I explain to a customer or user what it means for a feature to be judged important? Is that a fair breakdown?
Yeah.
Cool. So to the first question, this is actually overlaps nicely with what Paris was asking. Data scientists and data analytics specialists have to be really good at developing empathy for their end users. There's no way around that. You have to figure out, what does the person who's going to consume this actually care about? And a good starting point is dollars. Like, if there's a way for you to convert the value that your prediction has created in dollar terms, it doesn't matter, by the way, if you're an internal data scientist where you're making team products, analytics that are to be consumed within the company. So like, the end user is like your manager, or the end user is a developer, something like that. Either way, whether it's that or whether they're an actual user of the product who's paying, it's the same thing. At the end of the day, that person wants some unit of value from you. And very often, dollars are a great way to do that. So, if you're trying to predict, customer churn, right? This many customers are probably going to churn out with this probability. Like, just convert that based on how many customers, what the n is, multiply those two numbers together, or multiply in the cost per customer, and get the total cost to the company of having this many people leave, or whatever, stuff like that. Basically, as much as you can, you want to convert it into units that matter to the end user. So starting by thinking about that, like, if I gave you an answer, what are the units of that answer that would be most meaningful? And then try to express the problem in those terms as much as you can. And usually it's surprisingly easy. Like, usually there's some way to use a model to predict a number, and then you can multiply that number by another number and get something that's a lot more user relevant. Does that make sense for the first part?
Yeah, it does.
Cool. And then the second piece is very nuanced. It's a challenging question. How do I convey the feature importances, which, right, we talked about permutation feature importance in this case. And this would, it's tough because the question is a great fit for this session, but the topic of permutation feature importance is one that we'll dive into more when we talk about feature selection. In the short term, okay, what I'll tell you is this, and maybe this is something that will be helpful for those of you who haven't yet thought a lot about R-squared and correlation coefficients. So it's actually possible. You might wonder how it is that, like, a lot of models like random forest will give you an R-squared score. I don't know if you guys are aware of that, but like, you run a random forest, you can actually use scikit-learn's their model evaluation library to get an R-squared score from, like, your random forest, your neural network, or whatever. It's not just linear regressions that you can get an R-squared for. So what does the R-squared mean in that context? Well, R-squared, what you're actually going to do is, in those cases, you plot your predicted value against the actual value. And if you imagine, like, what that plot should look like, I mean, it should be very straight-liney, right? Like, if I predict a certain value, like, hopefully the true value is going to be linearly, or not linearly, but pretty tightly related. And so that R-squared value is actually what permutation feature importance by default is going to measure. So how does the R-squared value drop? If your model is better, then your predicted values are going to line up more closely with your true values, right? So as your model gets better, that R-squared value should go up. If your model gets worse, because, for example, you just shuffle the column that's super important, then that R-squared value will drop. So the question, when in the context of permutation feature importance, the question is, how do I explain R-squared to my end user? And I haven't put much time into thinking about that, frankly, but I think a pretty straightforward example would be show them, hey, predicted value, actual value. Like those are pretty easy to understand. If the model says that the value is going to be low, is it really low? If it says it's going to be high, is it really high? That's a fairly intuitive way to do this, but it only gets you so far, I guess.
Right. One way I've thought about it is, I don't know if it's true, but the average, if you take the mean of all your outcome variable, right, and you predict and you think that mean is the model, like no matter what the input, mean is my output. So that's one model, and then you have your real model, which is more nuanced. So how much better is your actual model as compared to that mean model? That is like your model completeness. Like if your R square is 60%, that just means that the inputs that you have captured only capture 60% of how much you can predict your output. So there might be more data, more variables that you need to capture to get that R squared further ahead and further distinguish your model from the mean model.
Yeah, I think like the question of how to explain these things is very much an open one, but I think that's a great strategy as well. Like, yeah, it's always tough to decide, like, is the answer graphical or is it mathematical or is it like, it's going to be a mix depending on who your stakeholders are. But yeah, I think that's a really good question and one I haven't thought enough about.
Great discussion.
Awesome. So maybe we'll leave it there. If you have other questions you want to follow up, feel free to DM me on Slack.